Una alegría poder presentar a Amand Lukas. Le conocí en 1975, cuando era yo estudiante de doctorado en Cambridge y nos llevaron a Bélgica para un curso especial con los mejores especialistas mundiales. Ya entonces él era un ejemplo de elegancia y finura que han caracterizado toda su obra. Belga, catedrático de física de la Universidad de Namur y profesor visitante en muchas universidades. Ha visitado muchas veces también los laboratorios IBM. En física en materia condensada es referencia obligada en varios campos, especialmente en el campo de la espectroscopía electrónica, por cuyos trabajos recibe en 1985 el premio más prestigioso de Bélgica, el premio Franklin. Es un gran didáctico, tiene libros deliciosos. Les recomiendo un artículo que acaba de salir, Garabatos que cambiaron el mundo. Parte de ello nos contará hoy. Pero también tiene una forma elegante y clara de describir toda la física envuelta, que está envuelta en la determinación de la estructura de doble hélice del ADN. Es un artículo bellísimo por el cual recibe en 2001 el premio Bernes por sus contribuciones originales a la enseñanza de la biología estructural. Los vascos somos muy aficionados, yo el primero, a apostar. Ya sé que aquí hay gente que juega muy bien al billar. Yo les aconsejo que controlen sus tendencias a la apuesta y no apuesten con el profesor Lukas en este campo, porque es un hombre que pertenece a muchísimas academias, entre ellas a la Academia Belga, a la Academia Europea, pero sobre todo es miembro de la Royal Academy de Liège de Billard, the Royal Academy of Liège of Billard. Don't bet with him, even if you are Basque. Thank you.
I don't know if I should sit here or...
No sé si debo ponerme aquí o aquí. Necesita un micrófono inalámbrico.
Thank you, Pedro, for the nice presentation. I don't know what you said, but I hope this... Okay. I just caught the billiard part. Thank you. So let me start by thanking this the organization of this sumptuous meeting, the President, the Vice President, and all the other people involved, especially Unai Ugalde, with whom I have corresponded for the last few weeks in a very, very efficient manner. Of course, Pedro, everybody knows Pedro and his efficiency. I know Pedro since 1975, when he was still adolescent. But now he's a full-fledged professor, very well known and extremely efficient in bringing science to his Basque country and to Spain. I'm going to speak about, like everybody else, I suppose, Einstein and diffusion phenomena that changed the course of human affairs. I suppose I owe you just an explanation of this bizarre title, Diffusion that changed the course of human affairs. I have been inspired by this quotation. People are quoting a lot of people here. And I like particularly this quotation by Stanislas Ulam, who was already mentioned this morning. In his famous book, Adventures of a Mathematician, he reflects on the nature of his discipline. And he says this: "It is still an unending source of surprise for me to see how a few scribbles mean graffitis, basically, on a blackboard or on a sheet of paper could change the course of human affairs. For instance, this citation is quoted by Richard Rhodes, who wrote a definitive history of the making of the atomic bomb in 1986, an absolutely fascinating book, where, of course, scribbles were made to change the course of human affairs. What scribble? E equal mc squared by Einstein was a scribble which probably Ulam had in mind when he wrote this, because Ulam was one of the mathematicians at Los Alamos working on the atomic bomb in 1944, 1945. So the content of my talk will be that scribble, the diffusion equation. Never mind what it means for the moment. And I would like to apply it to explain a few phenomena. The early global communication by William Thomson, better known by all of you as Lord Kelvin. I would like to make clear the relevance of this equation in the debunking of a few secrets of life, such as how old is the Earth. The same Thomson in 1862 used this equation to calculate the Earth, how old is the Earth. And of course, in 1905, Einstein used this equation to calculate the size of atoms for the first time in the history of sciences. And in 1958, a marvelous application of this equation was done again by these two people, Mendelssohn and Stahl, to determine what is the molecular way that inherited character are transmitted from one generation to the next. I doubt, however, that I will have time enough to speak about this particular fascinating topic, but let me tell you that I have gone through the exercise of writing a paper for this magnificent symposium, and I'm pretty sure that the organizer will make it available to you if you request it. And then I will perhaps also speak about the secret of death, that is the creation of atomic weapons, and how Frisch and Peierls in 1940, two physicists, used that equation to determine how much uranium-235 you need to make an atomic bomb. So let me start with early global communication. Homo sapiens electricus communicator. Homo sapiens who knows how to communicate electrically. This is a famous sculpture that everyone will recognize here. It's Rodin, Thinker. It's about contemporary with William Thomson. In 1880 or so, he created this fantastic sculpture. This is a thinker, but nobody has ever told me what the hell is he thinking about. Ah, if only this existed, he thought. And what was it? It was there. Because if he had that, what would he say? He'd say, "Hi, Mom, I'm cold," you know, or some such trivia that the telephone are now being used for. Now, but this was created by Rodin at the time where ships were laying telegraph cable across oceans. For instance, this is an engraving of a ship laying a cable here through the Atlantic Ocean, going from Ireland to Newfoundland. This is another one, local ship. And there are two key dates to remember here. 1858 is the first successful cable laying between Ireland and Newfoundland, about 2,000 miles of cable. And this was such a breakthrough that the Time of London, the newspaper, had a headline quoting, saying, "Distance between Canada and England is annihilated." We are in 1858. And the device worked for 3 weeks until someone made a wrong maneuver and ruined the cable. There was 270 messages successfully exchanged, and that was it. But, I mean, the promise of the technology was so great that pretty soon, 10 years later, there were 2 new functioning cables and a major technology was born. But the engineers and the entrepreneurs were not crazy enough to go ahead and lay a transatlantic cable and see whether it worked. Of course, they had a lot of experience with continental short-range and middle-range telegraph exchange. And in addition, they had, this is a cable structure of this time, it's about 20 centimeters in diameter. There is a core here in copper, which is a line, the telegraph line. There is some shielding, insulator, and then these big cables here are just a structural cable for preventing the thing to break. So William Thomson, what does he have to do with that? Well, he was an extremely brilliant theoretical physicist. And in 1866, after the successful use of several ocean cables, he declared, I believe people will exchange information instantly all over the world. This is 150 years ago, you know. And thanks to communication advances, which I have made myself, was not very modest, and others. And how did he do it? This was a theoretician, and Thomson considered the following theoretical problem. You have a wire, a telegraph wire. It has a certain electrical resistance ρ, a certain capacitance C per unit length. And then he wrote an equation for the propagation of a voltage pulse along such a line. And this is the diffusion equation. The second time, perhaps, that the diffusion equation was written in the 19th century, the first time having been by Fourier in 1822, I believe, for the diffusion of heat. V is the voltage at the position x at time t, and this equation by Thomson is valid only if the voltage is slowly time varying, that is adequate for slow telegraph, which is manual. And you should realize, especially the young people, that electrical communication were done in the 19th century not by electromagnetic waves, they hadn't been discovered yet, but by diffusion. And a few years later, 20 years later, Heaviside from Great Britain added a term. So here is the Thomson equation here, and then he added a term to take account of the inductance L of the wire per unit length in order to make this equation valid for time-varying signals, for AC signals as we call them today. And how did he do that, Heaviside? Well, he did exactly what Maxwell did by adding a term to the density current, to the current density, which Maxwell called the displacement current, but Heaviside did it independently for telegraphy. And there is a marvelous biography by Paul Neheen, Oliver Heaviside, Sage in Solitude, published recently on his scientific biography. It's a wonderful book. I recommend it to you because it's technically very good, and at the same time it's a good story. So now, what is the solution of Thomson's equation? Thomson solved the equation for the simplest situation. You have the wire here, and suddenly at time t equals 0, you inject a charge q at the origin, so you close the telegraph and you remove it quickly. You close the key and remove it, so you inject the charge q. How does the charge propagate along the wire? Well, it propagates according to this solution. You see here, Bill Gates has made us again something. This thing is square root here, square root, you see. That's what happened. So the voltage propagates diffusively, not by a wave. And if you sit at distance x from the origin, say 2,000 kilometers away from the origin, this is the kind of pulse you are going to receive. You will have a voltage with a maximum. The width will be about 1 second. The time of arrival will be about 1 second if you have 2,000 kilometers and you have this kind of diffusivity along the wire. So it took about 1 or 2 seconds for the pulse to go from England or Newfoundland to Ireland and vice versa. Now, this was Thomson and Heaviside, who Thomson invented the telegraph foundation, mathematical foundation of telegraphy, and Heaviside invented the mathematical foundation, the scribbling, for the telephone application, which uses much higher frequencies. And then simultaneously, of course, there was Maxwell working on the general propagation of electromagnetic waves, and Hertz defined that this is true, that there are electromagnetic waves propagating in materials as well as in empty space. And from these early electrical scribblers or doodlers came a tremendous amount of applications. Prodigious possibilities: radio, TV, radar, microwave, lasers, optic cables, cellular phone of today, GPS, and so on. So that was perhaps one of the first use of the diffusion equation. Now let me talk about the age of the Earth and the size of atoms and the structure of DNA if we have time. So the age of the Earth and the antiquity of life. Thomson was involved in that also. Thomson was a very versatile theoretical physicist. Of course, he was a thermodynamicist as well. And when he wrote his telegraph equation, he immediately noted the similarity with the Fourier heat equation, which is exactly the same formulae. Here is a voltage, there is the temperature of the medium where the heat is transported. So he said to himself, let me use this heat diffusion equation to figure out how long the Earth has been going on, assuming that, first of all, the Earth is a semi-infinite material here, pictured by this red rectangle, facing vacuum. So he used a one-dimensional Earth. He was not, mind you, a flat Earth advocate, but he wanted to use the linear diffusion equation in one dimension instead of 3 dimensions. And he assumed that at the initial time, the Earth is at 3,900 degrees centigrade. That is the temperature of molten rocks. And this is the initial condition. It's uniformly heated at 3,900 C. And now how long did it take for the heat to dissipate through vacuum and arrived at the present-day circumstances? That is, presently, these should be differential signs here. Presently, the gradient of temperature at the surface of the Earth is about 36,000 of a degree per meter. So if you go, say, 1 kilometer inside a shaft, temperature will have behaved by 36 degrees centigrade. That's what it means. That was known at the time. So this was a boundary condition here. And the other thing he needed is a diffusion coefficient here, which is the diffusion of ordinary rocks, 1.2 × 10⁻⁶ centimeters squared per second. That was measured. And with this, he could solve and ask, what time did it take to come to this surface temperature gradient? And the solution is T0 square, the square of the initial temperature, divided by pi d, d the diffusion coefficient measured, and then you have this surface temperature gradient 0.36 degree per meter square. Calculation, 100 million years. A black eye for Darwin, because at that time, 1862, Darwin has just published his evolution of species by natural selection, and he said this: "I am greatly troubled at the short duration of the world, according to Sir William, for I require for my theoretical views a very long period before the Cambrian formation." Now, what is he talking about? Let me show you here an amusing spiral timeline. We are here at present, and then you spiral down several times all the way to 4.5 billion years. And the Cambrian time is between about 500 million years and 550 million years. That's the Cambrian. It's called the Cambrian. I don't know why, but it's well known as a Cambrian formation where you can find practically all animals, all sea animals that exist today in fossil form. And of course, Darwin needed a very long time before the Cambrian explosion. It's called like this, a Cambrian explosion of life. He needed several billion years perhaps before evolving all these complex structures that were shown in the Cambrian formation. But Kelvin said, oh, the Earth is only 100,000 years, that's 65 million years here, the KT boundary where the dinosaur disappeared, and here is 100 million years. So that's much too short. So what's wrong? Of course, for 35 years, there was a tremendous controversy. Who is right? Is it Darwin or is it Thomson? And of course, this had very big repercussions, not only scientifically, but for religious questions. Now, what was the trouble with Thomson's model? He used the Earth as if it was a homogeneous sphere. Of course, it's not a homogeneous sphere, as we know. And someone, 35 years later, Perry, came up with this structure. He added a thin, low diffusivity shell of a few kilometers thick in 1895, so 30 years practically after Thomson's model. And with this trick, with a low diffusivity, the heat would have hard time to escape, and then he could raise the Earth time, the duration, to billion years. Of course, we know now that in addition to the thin shell, there is a radioactive mantle. Only months after the Perry Heaviside calculation, someone discovered radioactivity of uranium, this Henry Becquerel, in 1896. That changed completely the situation, because now there was a source of heat to keep the Earth cosily warm for billions of years. And this heating of the Earth is lacking in the diffusion equation. You have to add a source term in order to take that into account, which Thomson didn't. In addition, there is other things. There is a molten core inside, and how does one know that, by the way? Well, via another scribble, magnificent scribble, which is a wave equation of classical mechanics. And there is a solid pit that we know also exists because of the analysis of seismic waves and so on. In addition, in the early 20th century, continental drift was discovered, and pretty soon it was ascribed to plate tectonics, that is, to convection movement in the mantle. And of course, convection invalidates completely the diffusion equation, because diffusion assumes that there is no transport of mass, like in convection. So the cure to this controversy occurred progressively, and now the calculation of the age of the Earth on this basis is done completely differently. Now we come to Einstein proper. What I talked before concerned two applications of the diffusion equation before Einstein. Now what about Einstein? In 1905, he supposedly explained the Brownian motion. What is the Brownian motion? In 1828, Frederick Brown, this is an engraving here, Frederick Brown, with this microscope, which is a very simple affair, it's just a single lens. The sample is here, you look through the lens, there is some light coming through that mirror, and he observes the Brownian motion, which I'm going to show you in a minute. But in addition, in passing, I should add that Brown also observed the structure of plants, tissue, and in particular, he discovered that in the middle of these cells that had been discovered by van Leeuwenhoek several centuries before, these cells have something peculiar in the middle, which is called now the nucleus. So with this microscope, he discovered the nucleus, not only the Brownian motion. And here is a movie of the Brownian motion that probably very few of you have ever seen. Let's see if it's good. This is a Brownian motion. So a technician at my university was requested to put some India ink in water, put a drop of such ink under the microscope, a very good microscope, look at it, and this is what you see at room temperature. So you have these particles of India ink dancing around, and you can see that, oh my God, my laser quit. So you see that the small particles dance energetically, the big particle hardly move. Come on. No laser available? I have a laser here, but now it's stuck. Sorry. So you see the small particles, smaller particles which move very rapidly, erratically in all sort of direction. The big particles hardly move. Some of the particles rotate as well as move frantically. And this goes on and on and on forever. This is called the Brownian motion. Incidentally, I am curious to know how many of you have already seen that. Can you raise your hand? Can you raise your hand, see who has seen the Brownian motion before? A few tens of people. Thank you very much. The amazing thing is that Einstein never saw that. He never saw the Brownian motion. I don't think Einstein ever cared to look through a microscope. Professor Holton will correct me if otherwise. But at least in 1905, he had no idea even of the existence of the Brownian motion, because he writes explicitly in his paper, I am predicting the motion of particle suspended in a fluid. And at the end of the introduction, he says, maybe this coincides with the Brownian motion, but he says, the information I have at my disposal is too poor for me to have a clear opinion about that. Now, if you were to give that to a referee these days, you would be kicked back, you know, and you would be said, why don't you study the literature? 75 years of literature on the Brownian motion that Einstein simply ignored, because he preferred to rely on thought experiments, on the experiment in his head. You know. And of course, this was a Brownian motion that he predicted. Sorry. Oops. So Albert Einstein, in 1905, he wrote three basic papers that we are celebrating this year, and I have summarized them in three existence statements. Ether does not exist. That's relativity, the most important consequence being E equal mc squared, perhaps. And the second paper it says photon exists. That's a photoelectric effect, equal h nu, h is Planck constant. And the third one is atom exists. That's the Brownian motion paper. A thought experiment. So in his paper, Einstein solved the following thought experiment. He imagined that he has a vessel here, and that at the x equals 0 plane, at the plane x equals 0, he put some particle distribution, homogeneous two-dimensional particle distribution at x equals 0. Perhaps it's a sheet of sugar that you put in water. Then when you do that, a sugar molecule go away, start diffusing. After some time, they have a distribution which looks like this. And he asked himself, what is the distribution of particle after time t in the vessel? And he derived the diffusion equation for that, and he found a solution. He derived that simple equation, which is just the same as Thomson or Fourier equation. It's a linear diffusion equation with a certain diffusion coefficient here. I don't need to define. And he solves it, and he gets this equation, of course, again. He gets this distribution, which is a Gaussian distribution of particles after time t with Gaussian width measured by 2 dt. So with this, he says, I can measure the Gaussian width, and by just measuring the mean square displacement of one particle, microscopists can do that, and you will find root 2 dt according to this equation. And since you know the time, you measure delta, you get a measurement of the diffusion coefficient of the particles in the fluid. And he insists in his paper in 1905 that this is a universal reasoning. What diffuses in what is entirely represented by this diffusion coefficient. It could be particle in water, it could be even molecules in a solution, it could be neutrons in a spherical piece of nuclear material, it could be anything. As soon as you define this magic symbol diffusion coefficient, then you have a problem of diffusion. And then, on the other hand, in this same 1905 paper, he calculates the diffusion coefficient. This is a way to measure the diffusion coefficient. Now he says, I'm going to calculate it for spherical particles which swim in a fluid of viscosity eta, and that he showed that for such particle, because of the Brownian motion, they exert a pressure themselves, which is called the osmotic pressure. And the osmotic pressure, he demonstrates in the paper that it obeys the perfect gas law, P equal N K Boltzmann T. So he does a tremendous amount of things in his paper, and from that he deduced the diffusion coefficient as a function of temperature, viscosity of the liquid, and the radius of the particle. So by inverting this, he could do two things. First, calculate the Avogadro number. I believe that Professor Hirschbach will talk about that much more, and also perhaps Fernando Flores. And then he deduced the atomic dimension R by inverting this formula. It's given by this, and here on the right-hand side, say for a sugar solution in water, everything is known. Temperature, viscosity of water, diffusion coefficient of sugar in water. You can even measure it at home in your coffee cup. And then you get the radius of 0.6 nanometer by applying this, the 6 angstrom. Very reasonable value. Now, let me see. I'm going to skip that because it's rather technical, and I'm rather going to the atomic bomb story. Homo sapiens atomicus deleticus, that is, Homo sapiens who knows how to destroy himself with atoms. Oh, sorry, go back to, okay, thank you. Oops. See, let me go back. Now, this is a famous picture of Einstein here on the left and Leo Szilard on the right. Leo Szilard was a theorist from Budapest, a Jewish person escaped from the Nazi influence in Europe already in 1934. And he was a refugee first in England and then in the United States. He was a good friend of Einstein, had a couple of papers with Einstein, so they knew each other very well. And he went to Einstein to tell him, well, fission has been discovered by Germans, Otto Hahn and Fritz Strassmann 6 months ago. And what is fission, asked Einstein? Well, it is chain reaction. And he exclaimed, my God, I had never thought of that. Daran habe ich gar nicht gedacht. He never thought of the possibility of a chain reaction. Professor Holton will correct me if this is about the fission that he said this remarkable utterance. And Szilard had another utterance as soon as he learned about fission and the neutron emission by the fission process. He said, humanity is heading for grief. And indeed, grief there has been because of the fission problem. Now, what did the letter say? Well, what happened is that Leo Szilard was there with a draft letter written by Szilard, Wigner, and Teller, who were 3 refugees from Budapest. And what does the letter say? And they said, look, Professor Einstein, you are the most important person scientifically with the more weight. Why don't you read the letter and sign it, and we'll discuss where to send it to. What does the letter say? The letter said that nuclear reactors for energy production are for the immediate future. So the letter is August 1939, 6 months after the discovery and explanation of fission and the discovery of the secondary neutrons emitted by fission. Second, fission bombs are possible, but far less certain, because it required uranium-235, pure. And nobody knew how to separate uranium-235. By the way, uranium-235 is separated these days from uranium-238 by diffusion, by a centrifugation process which relies on diffusion. 3, Germany has taken over Czechoslovakia, and in particular the uranium mines. That's written in the letter. And 4th, he invites political authorities to create programs to support physicists and chemists and scientists to work quickly on fission, because the Germans are also doing it. The Nazi Germany is probably doing it. But to whom should it be sent, this letter, he asked Einstein. Well, we should discuss that, he said to Szilard, who had an idea. But Einstein said, oh, I know to whom we should send it. We should send it to the Queen of Belgium. This is Queen Elizabeth here, with whom Einstein had very privileged musical, artistic, and scientific relations. He came to Brussels once in a year about to play violin with Queen Elizabeth. He would come out of the central station in Brussels with his bare feet in his sandals, would step in a taxi and say, take me to the Queen. And he would look upon, frown upon, of course, until he was recognized as the great Einstein and was indeed uttered in the palace. So he said, why don't we send it to the Queen of Belgium, an insignificant land in the middle of Europe? Oh, but not so insignificant, because it so happened that Belgium had at its disposal the Belgian Congo, where there were mines of extraordinary richness in uranium, and which was exploited by a firm in Belgium. And perhaps this is what Einstein thought, that it should go to the Queen and the King of Belgium in order to try to have special prices on uranium ores. But then Szilard said, no, this is a bad idea, because we should really go to the big fish. We should send it to the President of the United States. And that's what they did. Einstein signed this letter, and it was sent to Roosevelt, who, upon reading it, said, action. And that was really the start, the slow start, but the start, nevertheless, of the Manhattan Project. Now, what does the diffusion equation have to do with all this? The diffusion equation is rewritten here once more. Time variation of the neutron density in a fissile material is the diffusion coefficient times the second derivative, spatial derivative of the density. This is pure diffusion here, but you have to add a term, because of the fission, are going to create extra neutrons. Every time a neutron penetrates U-235, it creates 2 extra neutrons, so nu here is about 2. And tau is the time between successive fissions. So this is a source term of the kind that Thomson should have added to his equation to take account of radioactivity. And the source term is proportional to the density of neutron present. This is very classical in population dynamics, that the rate of production of something is proportional to the genitor, so to speak, and inversely proportional to the time it takes to generate a future generation. So now the question is, how do you solve this equation for a spherical piece of uranium-235, say, of radius r? You have to add a boundary condition. And you write a boundary condition which is explained in the Los Alamos primer here. It's a little book, fascinating, published, written in 1943 at Los Alamos as an instruction basis for the scientists arriving in Los Alamos. It's published in 1992 for the public at large. And they discuss various boundary conditions, one of which is this one, never mind about the details. But then they solve, and this is an elementary exercise for freshman physicists or chemists to do. And they found this minimum radius for an explosive reaction to occur in a sphere of uranium-235. 2/3 pi square, root pi square, diffusion coefficient, generation time divided by nu minus 1, and this is about the diffusion mean free path. Now let me go back to the previous picture and compare the result of this calculation that was used by Frisch and Peierls in March 1940 in a famous memorandum that these two people addressed to the military and political authorities in Great Britain in order to tell them, be careful, there is a possibility of creating nuclear bombs, and probably these two people came from Germany or from Vienna. They knew that although a lot of very highly competent scientists had gone away from Germany, in Nazi Germany, there remained plenty of scientists who knew what to do. And indeed, the Germans created a program of research in fission, which is called Uranverein, the Society of Uranium, which unfortunately went nowhere in creating an atomic bomb. But in 1940, Frisch and Peierls made this calculation I just sketched. That is, what is the size of a sphere of uranium-235 in order to have a an explosive chain reaction. I'm sorry. And this is the assumption that they made to solve the problem, compared to, in red here, the assumption you can find in the Los Alamos primer, which are better nuclear constant, which use better nuclear constant. They assume pure uranium-235, that's okay. They assume a multiplication number 2.3 neutron per fission for U-235, that's about okay. They assume no scattering, just fission. So that is, every time a neutron comes to a nucleus, it splits it, it makes fission. That's not the truth. The total cross-section for anything happening is 4 × 10⁻24 centimeters square, while the cross-section is something of the order of the area that the particle, the neutron here, sees when it encounters a nucleus of U-235. And the fission cross-section, they assume fission pile of 10⁻³ centimeters square, much too high, 6 times too high. The true fission cross-section is 1.5 × 10⁻24 centimeters square. Most of the cross-section goes into other, elastic scattering, inelastic scattering, and so on, but not fission. And finally, the uranium density that is used in the memorandum is incredible, but it's 15 grams per centimeter cube. The true number is 19 grams per centimeter cube, but such was the hurry that they did not check the number. So the result of the calculation was that the fission mean free path was only 2.6 centimeter, whereas in reality it's 9 centimeter. The critical radius was 2.1 centimeter instead of 5 times as much, and the critical mass was 0.5 kilogram in the memorandum, 0.6 kilogram. In reality, it was calculated to be 60 kilograms, 100 times larger 3 years ago in Los Alamos. But this is this over-optimistic evaluation of the critical mass which persuaded the military political authorities in Great Britain to go ahead and start the nuclear research program. And of course, because the UK had a privileged relation with the Americans, started really to give impetus to the Manhattan Project in the United States. Now, my time is about over, isn't it? So, in the Heisenberg, in the German program, the Uran-Verein, there were a very important person involved. Hahn, discoverer of fission. Heisenberg, creator of quantum mechanics, was the head of the scientific head of the Uran-Verein. He played a very important role in this story, and he played a role which partly explained why the Uran-Verein failed to produce even a reactor. But this is another story, and I better stop here just by concluding that this simple linear diffusion equation occurs in several places, in many places. I have selected a few of them here, because those phenomena which I have described change the course of human affairs. In particular, the one I have not described, the one which concerns the way we in ourselves replicate our DNA, is also an example of very great historical interest. And I was asked at the interview half an hour ago, how comes mathematics is so important to understand physical phenomena? And this is just what Einstein asked himself. How is it possible, he said, that mathematics, something that we invent in our mind, totally independent of experience, how should such mathematics have so relevant to natural phenomena? He asked the question, but he never provided the answer. And of course, many scientists, famous and less famous, philosophers, and ordinary people, thinking people, ask the same question. We don't know really why mathematics is so relevant to describe natural phenomena. Perhaps the easiest answer is that we are part of natural phenomena. Our brain is a natural phenomenon, and therefore there is no mystery at all. Still, a lot of people ask the question, and maybe you have an original answer. Thank you very much.
To answer questions.